Good evening, everyone. I welcome you all again to the second session of this doubt session of the course Basics of Finite Element Analysis, Part 1. So, as discussed in the last class, I would just repeat the way we would hold these meetings. It would be first I would just summarize quickly whatever the content that has been covered in that current week, and then we'll discuss the doubts after that, and I'll also discuss some relevant questions that would help you with your assignments and understanding of that week's content. And your doubts can come anytime in between of this summarizing session or after that or even between the question part. So in week 2 we started with covering the key concepts, some basic concepts and terminology that would be used again and again in this course. So firstly, in a given differential equation we have something known as dependent variable and independent variable. So basically the field variable that is the solution for which we solve the equation. In this case, it's the variable u here that is the dependent variable because it depends on other variables such as the position, time, etc. And the other variable that is the position here, that would be an independent variable. So that position is defined independently, not dependent on any other variable. Similarly, we would have time variable that would have been an independent variable. The next term would be the domain. So basically, domain is a collection of points such that for each point, the neighboring point, a point whose neighboring point is also in domain. So this basically this type of definition helps us to distinguish between a domain and its boundary. It's talking in colloquial language, basically whatever the area, or in case of 1D it's 1D segment, or in 2D it's an area, in 3D it's a space. So whatever the area is under consideration of our differential equation, that is called a domain. So a domain is known as can be of type which is known as convex and simply connected. So convex is basically the convex we have that we study in case of mirrors and lenses. So if we draw any line within a domain between any 2 points in the domain, then that line should always be inside the domain. That is known as a convex. So the first example is a convex and simply connected type domain. And the next example here, this one is not convex and simply connected. So since it has a concave surface here, so if we draw a line between these 2 points here and here, so that line would have some part of it outside the domain. Then we define something known as a function of class M. So this kind of definition is useful when we are deciding our shape functions, shape variables. So the definition of this the function of class M should satisfy these 2 points. So firstly, the function should exist at all points in the defined domain. So when I say in the defined domain, in order to define the class of function, we need to define the domain first. So say a function should not exist in the whole sequence of real numbers, but it might exist in some part of that real number domain. So if we define the domain in such a way that it exists, so it would said to be existing in that domain. And the second point would be it should satisfy that all partial derivatives till mth order of this function should exist and be continuous in that defined domain. Again, the domain should be defined first. So as in the class, the example was given for the sin x function. It can be it differentiated any number of times, infinite number of times. So its class is C infinity. And then we have various types of problems that we solve. First one is the boundary value problem. Then we have initial value problem. Initial value problems basically are time dependent problem. So we need to define the solution. We need the solution initialized at the time that the initial time step equals 0. And we have eigenvalue problems. These are basically mixture of these two. uh, we would get better understanding of these types of problems once we deal with it once we go ahead in this course. So yeah, the next part we come on is the weighted integral residues. So in first week we studied that in finite element method we approximate the solution variable by an interpolation of certain functions which are known as shape functions. Uh, so here we have chosen some simple differential equation problem. It's a boundary value problem. The boundary conditions are defined here. It's the domain defined for this problem also here. So as uh, as discussed earlier, we have approximated the solution vector as follows here by certain uh, known functions, and the variable cj would be unknown. So one thing to be noted in choice of these functions is that the functions should be chosen in such a way that the boundary condition should be satisfied. Okay. So boundary condition is something that is not automatically incorporated in the differential equation. If the solution is satisfying, if this solution is satisfying this differential equation, doesn't mean it automatically satisfies the boundary condition as well. So it doesn't. It is not necessary. So the choice of these functions should be in such a way that boundary condition is automatically satisfied. So we have chosen the for this problem we chose the solution in certain way. It's for discussed in the class. So I'll just quickly go through it. So the next step would be to plug in the this solution into the differential equation, and we get some a polynomial of something like since it's a three degree polynomial here un, if you substitute in the equation, then you have direct u term here, so you definitely get a cubic term, plus we have square term, then we have square term, and then we have simple term. So to satisfy this condition, we have need to have separately put the all these variables equal to all these coefficients equal to 0. So this would give you, so these coefficients alpha beta gamma delta would be some function of these variables c1 and c2. So this would give you whatever the number of equations would be for c1 c2. But we saw in that problem that the uh, the 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 equations that arise from this system, they were not consistent. So since if we have more number of equations than variable, and the so if it's four equation for two variables, the two of those equations should be uh, so two of those equations should be some form of other two equations. So we should only have two equations for two variables. So if they are not convertible to other two equations, that system is inconsistent system of equation. Such system is not solvable. So what we saw was not solvable system of equation. So we came to a conclusion that consistency of this that system of equations was dependent on the choice of these functions. If we would have taken the exact choice of the correct choice of these functions, such that the residual means the left hand side of that equation should have been 0 at every point. But what the choice we did right now, that didn't give us the correct residual 0 at all points. So that is the problem. That is the problem in going with the exact solution. So we can't have we can't just choose random polynomial functions and get residual 0 at every point in the domain. Not possible. Any function, right? So instead, what we can do is, as discussed in the in first week's class, we instead of getting residual 0 at all points, we can what we can have is we can get the weighted residual 0. So we can minimize the error in the entire domain. So residual error means residual. We can minimize it, so such that the integral of this weighted function multiplied by this residual would give 0. So once we follow this procedure, we will get some algebraic equation from this, some equation of some a times some alpha times c1 plus beta times c2 equals to gamma, something like that. So and how many number of variables we are solving, so c1 c2, we can choose that many number of weight functions, and we can get that many number of equations. So this type of system is easily solvable. So we choose a number of weight functions equal to the number of unknowns. So this approach is what is known as variational method. So in variational method, we basically multiply the residual of the governing equation with some weighting function and integrate it over the domain and equal it to 0. And by switching the weighting function every time, we get as many as many equations as are required. So yeah, so the next thing we studied this week was integration by parts. It's basically basic technique where we learn in I think 11 12 maybe. So I'm not going to explain the integration by parts to you. It's basically simple formula here. But the application here, why do we need integration by parts here in this problem? So basically, we would appreciate it when will solve these problems. So the main application of this integration by parts is here is that we can transfer differentiability. So suppose we have in the first term in this equation, we have this derivative of v. So integration by parts allows us to transfer this derivative from v to w here. So this is basically allows us to weaken the differentiability requirement in this weighted residual statement. So this doesn't this term looks like what we had in this weighted residual statement, right? So we finally we get reduced differentiability in the variable. So in our governing equations, this term here is not first derivative; it's usually second order, usually second order. So when we do integration by parts on this term, we get we reduce differentiability on this term and add it to the other term. Also, if we have, so I'll show you here. If we have say w here, e square d by dx square here. So if we perform integration by parts here, we will get a term dw by dx, dv by dx. So we have same type of differentiability on both these functions w and b, and you'll see in when we choose the shape functions and weight functions, if we choose the same nature of function for both v and w, if v and w would be same type of functions, then this there will be symmetry in this term here. And later when we'll solve these problems, we would see that we form matrices based on this very term. We form matrix, and this would help us form symmetric matrix. So we have one and one here, two here, like that. So we'll have 1 2 here, 2 1 here. So this time we'll have symmetry in the 1 2 and 2 1 term based on this term. So yeah, this helps to get us to get symmetric matrix. And why is symmetric matrix useful for us? Can anyone tell here? Uh, you can unmute yourself and answer. Why are we so excited to get symmetric matrix? Anyone listening? Am I audible?
Yes, sir, you're audible.
Yeah. So can someone answer this? Why do we need? Why are we so excited to get symmetric matrix in these problems? Anyone? You can don't be shy. You can. It's fine if you don't answer it correctly. Solution can be easy. Right. Right. So yeah, exactly. Solving symmetric matrices is very easy. Very easy. So the algorithm built for symmetric matrices are simpler. It's it. In unsymmetric matrix, it's very pain. So yeah, so this is the advantage of doing integration by parts. So we reduce the differentiability requirement on some variable. So okay. Tell me why are we reducing differentiability requirement for solutions? Someone among you, please answer this. You're welcome to unmute yourself and answer. It's fine. So my question is, why do we want to reduce differentiability requirement? That's my question. Anyone? Just give a try. You can guess. Complexity decreases. Yeah, but what do you mean by this complexity? Yeah, I get it. Complexity decreases, but what do you mean by this? That's my question. What kind of complexity? You can unmute yourself. problem very few assumptions. Mm, Problem with very few assumptions. Uh, you're going too far away. I think you the answer what I'm expecting is very straightforward. So I'll tell you then. Yeah, some function can be complex, but in FEM we don't go for complex functions. We just take simple polynomials. We just don't deal with anything complicated. So taking derivative polynomial is not a very big thing. But the thing is, if you have a second order, sorry. So if you have a second order derivative here, so in FEM we assume solution. So we would have assumed a function for v, right? And if if we assume a constant or linear function, this would blow up, right? This would second derivative both these functions would give zero. We take second derivative, both of these would give zero, and this would blow up the whole solution. So that's why we studied class or function earlier. I'll just go back there. Yeah, function of class M. That's the reason that we study. So we don't want our equations to just blow up to zero. We would be This would be a redundant equation. So we would need at least a second degree polynomial, at least something like that to get us a non-zero value in the second derivative. So why are we wasting our resources and time in this complicated assumption? So this is basically the advantage of reducing differentiability, right? Was that fine? So we reduce the differentiability in order to assume a simpler function. You were in a way right, simpler, but this is the whole you can say wisdom behind reducing differentiability. I hope this was understood. If there's any doubt there, then you can ping me. You can unmute us and ask and or just drop a message. So the next thing we studied this week was gradient theorem. This is also something fundamental we had studied in first year of graduation, I guess. Basically, there are two theorems: gradient theorem and the divergence theorem. Gradient theorem is useful for a scalar function, and the divergence theorem is for vector function. So basically, estimate estimates the boundary phenomena from the some inner phenomena, right, and vice versa. So why do we need gradient theorem here? So gradient theorem is basically you can say a parallel of integration by parts in 2D or 3D. So we we could perform integration of by parts on this kind of equation in which is in 1D. So integration by parts is easy here. But suppose if I get some equation of the form, you can say, sorry, if we get an equation of the form, so del square u by del x square, del square u by del y square plus u equals 0. So this would be a won't be able to be dealt with integral parts, even if it can be, but it would be very complicated. And the equations that we usually see in real application are much more scary than this. So this here we see in this step how we can reduce transfer different, just like we transfer differentiability in integration by parts in 1D, we can transfer differentiability here. We can see that differentiability at this term is transferred to this term here, with again a boundary term coming up here. So you would see here we have an integral, but where's here we don't have an integral, right? So don't see it in that way. It's basically a boundary term. In case of 1D, the boundary is just value at 2 points, right? This point here and this point here, A and B. So that's a boundary term. I'll get BT here. So similarly, this term is also a boundary term. The integral is defined on the surface of the domain, the 2D domain. So this whole is gamma boundary. Okay, so yeah, the gradient theorem and both divergence theorem are useful to transfer differentiability from one function to another. So in reality, we usually have second degree operator here. So the equation that I wrote this stuff up here. Okay, I deleted it. So that equation could be in second degree, it could be written as this. Sorry, not second, in 2D, like in vector form. This equation can be written like this. So in this case, we have a second degree of the gradient here, and we can transfer the derivative like this. So this reduces the differentiability requirement for G, and we get symmetry in W and G. So yeah, this method is useful for finding. Okay, I didn't mention weak form, right? So whatever we get, whatever equation we get after reducing differentiability, uh, that equation is not known as the weak form. Uh, that has been discussed in the class. I'm just reminding you. So weak form means the differentiability requirement is weakened. So next we have functional. So basically, functional is technically talking. So no, I'll not start with technically. Functional is basically uh, an integration. Basically, it is said to be a function of function, but there is an integration always involved. So that at the end you will get some scalar value. So basically, mathematically talking, it basically maps u into a scalar I. This this would be a scalar known value, not a function. Scalar constant. So all these values xa, xb all are known. Only this u is unknown. So we studied what is known as what is a linear functional. So linearity has two conditions. I'll those two are summarized in this statement, but I'll separately write these two. So number one is we have L of u plus v. These are two some field variables. So that we give L of u plus L of v. And the second condition is multiplication with a scalar. So alpha is a scalar constant. So that can be written as alpha times L of u. So this is the condition of linearity. If you this concept of linearity is universal with anything functional or we have transformation, all these things. So anywhere you ask if anything is linear, you just check for these two conditions. If they are satisfied, straight away linear. If they are not satisfied, non-linear. It's very straightforward. And then we have bilinear. So bilinear functional basically has two but as the name bi suggests, it has two variables involved in this functional. So the whatever the operation is on both whatever the operation is on these two variables, and it would be linear in these two. So linearity would follow for individually for each of these. And symmetric bilinear is we know linear, we know bilinear. So symmetry is basically determined by this term. So I think that was it for this week's session. This was all that was taught in the video, the lectures for week two. Now, if you guys have any doubt, you can you can unmute yourself and ask, or I would just start with the some problems. I'll wait for some time if anyone wants to ask something regarding this, anything from this week or regarding whatever I just explained in summary just now.
Sir,
Yeah, yeah. Tell me.
sir, previous, sir, due to some circumstances, I didn't, I'm unable to attend some previous problem solving sessions, sir. So, how can I get access to it? Any links or something?
Access to what? The last session.
Yes, sir, previous sessions.
Okay, okay. Haven't they shared the YouTube URL or the Drive link or anything for the videos
No, sir.
from the NPTEL team? Okay, it's not there. Uh, what you can do is I can share it with you. I have those. I have actually uploaded all the last meeting video. I've recorded and uploaded on YouTube, and it's also there on Google Drive.
Okay,
Uh,
sir.
I thought that the NPTEL team would do the sharing thing. Anyways, uh, you have my email ID.
No, sir, I didn't have.
Okay, just give me a minute. I'll just share the URL. Just
Okay,
give
sir.
me. I'll share the URL in the chat here.
Okay, sir. Thank you, sir.
Yeah, just a minute. Where was it? Okay, I have it. Yeah, I have just sent the. See if you are able to access uh, the link, and if there's any problem, let me know. So, have you got it? Just confirm. Hello.
Yes, sir.
Okay.
It's a YouTube video link.
Okay. Okay. Yeah. That's for the last session.
Okay, sir.
You can
Thank you.
also contact the NPTEL team. We have uploaded the meet these slides and the recording also on the Google Drive. We have shared the links with the NPTEL team. You can contact the NPTEL team. They can give you these links,
Okay, sir.
or you can personally email me also. That's fine. Okay.
Sir, email
So
ID, sir.
I'll write it here.
Yes, sir.
You can contact me, and
Okay, sir.
I'll share the link with you if you don't have it. Anyway, so if there are no further doubts, we can start with some questions I have come up with to help you for better understanding.
Okay.
Just give me a moment. Excuse me. So for so we come to the first question straight away. So we studied about the class of functions here. So I want you to answer to figure out the class of these functions in all these sub questions. So first we have this function. Okay, I'm not just okay. So we have this function here, x to the power plus 4 plus 3x. And just as I told you in the class moments ago, that you need to define the domain also. So the domain here is real number. So it's this function is that, so we want to consider this function for the entire range of real numbers. So yeah, tell me what would be the class of this function. I want answers from you guys.
So class is 4.
Yeah, right. So the class of this function would be four. And for this next function, yeah, please answer for the B part, e to the power x.
1, sir.
Why one?
S- whatever number we replace in, uh,
So
I don't know.
firstly, verify if is this function e to the power x, is it completely defined in the our domain, that is real number? So is it completely defined in the whole range of real numbers?
No, sir.
Why exponential?
Sir,
If I draw the curve, the graph here, how does it look? Something like this, right? So is there anywhere that it's not defined in this whole range of domain? So we have plus infinity here, we have minus infinity here. There's no way, right, that this would be defined. This is not defined. Exponential is defined everywhere. So the first condition fulfilled. Then the next condition is how many derivatives of the exponential function are all defined in this in this domain of real numbers. How many derivatives can you take? So first derivative of this function would be exponential would be
e power x.
yeah e to the power x, right? So exponential doesn't change. So how derivative we take, we will always get e to the power x, and it is always defined as normal. So yeah, someone answered in the comment. It's infinity. Okay, and so the part C, log of x in real number. Yes, someone answer. Please, it's 2. Why 2? Can you explain? So first question would be, uh, is the function defined in this entire domain that I've defined? It's not defined. So its class would be zero. Okay, it's not defined in this domain. However, uh, we have if we modify our range from instead of real number, if we define our range from this one, okay, it's basically L. Okay, let's see, natural log. No, not natural log. Log base 10. If we it's basis 10. If we define a domain from here to infinity, now what would be the class of this function? This part that's part D, infinite. So we have to see how. So the first condition now is satisfied, right? It's defined in the in this domain, and so if we take first derivative, so the function f is log x, so f dash is 1 by x, f double dash x is minus 1 by x square, and so on. But 1 by x, is it defined in from 1 to infinity? 1 by x plots. So if you see, if you draw plot 1 by x looks something like this. So the only place it's not defined is 0. So from 1 to infinity it would be defined. So yeah, this is valid. Minus 1 by x square is also the same, and we'll just increase the power of x and negative. So I think we can go on till infinity, right? So yeah, someone answered that this would be infinity. If there is any doubt, please you can stop me anywhere.
I'm unable to understand the e power x curve, sir. Like, how did you draw it?
Mm, e to the power x. So you mean how I got this curve right here?
Yeah, like, how did you come to the conclusion that it belongs to a real number domain?
So real number. Okay, you mean how? Why is it defined anywhere in real number? So I would say it's just basically rather I can't explain it in very detail, but you can take any number. So sorry, yeah. So you can take any number for exponential. So for any positive value, we get some positive value, right? And for any negative value, we basically get 1 by of that positive value. That's the property of exponential. And the the maximum value for maximum value of exponential at any value in domain, there's no limit. It can go as high as you want. But in a negative direction, it would slowly tend to zero. So at the point of minus infinity, it would slowly reach to zero, and until then, it would be defined everywhere. So that's why I straight away concluded that exponential is defined everywhere in the domain.
Yes, I understood. Thank you, sir.
Yeah, no problem. Okay, so we'll go to the next question. So for a given boundary value problem, so this is some problem d square u by dx square minus fx equals to 0, and the boundary conditions define this. If we assume the solution un with some interpolation of some function pj, what do you think would be the suitable choice for some shape function pj among these options? Which one do you think would be most feasible choice? And why, of course, why? Any guess? If you get any answer in the chat, I'll just check. No, not yet. No idea. If you had to guess, what would it be?
So the option D, I guess.
D. Okay, why is it so?
Like my thing, I am thinking that d square u minus dx square minus f of x is equal to 0, right?
Mm-hmm.
So you have double differentiation there. So you cannot have a single variable there, like x or x plus 5.
Okay, yeah, that's a good one. That's a good one.
You should have a square so that double differentiation will come down to a single number like 5 or any other single digit.
Yeah, that's a good idea. Uh, but there's one more thing to it. That the boundary condition here is at the u equals to 0, you should get the value is 5. So, so whatever the choice of function would it be, uh, when x equals to 0, you should get u equals to 5. So, I, I guess that the first option won't be able to fit with this. The second also won't be fit with this, and even the only one that can do this is C. That's right, but as per what you answered, that this function wouldn't be able to fit in this. It would be it go 0. That's also a right thing. So if we have to consider this thing, then this would also fit. And again, the last one would not give 5, would give 25 at x equals to 0. So none of my option worked out. Yeah. This basically is simple exercise to help you explain that considering the shape functions, we need to first ensure that the boundary condition is satisfied. So yeah, we did integration by parts. I won't go into detail for this question. That's simple exercise. I want one of you to answer this. I'll give you some time to solve. Well, I'll also try. So what we do is transfer differentiability for x, we will take derivative of x, and we'll take antiderivative of sine x, that is minus cos x dx. plus we don't take any derivative and we again take antiderivative of sin x plus we get some constant. So we get here the plus dot integration of cos x dx, and that would give us minus x cos x plus sin x. Okay, that's not 0 to x, that's x. That's basically a indefinite integral. So that answer was right. So we'll get the antiderivative of cos x, we'll get sin x plus, no, sorry, minus x cos x plus, yeah, it's basic simple integration by parts. So now I want you to find the weak form. Some differential equation I found interesting. Schrodinger wave equation. So in Schrodinger wave equation we have this as dependent variable and x is of course our independent, and all these are constants. You can just replace all these by some, even this is also, you can replace all this by some constant. So what we'll have is we take weighted residual statement first, multiply the whole function by del phi, and we'll integrate for the, say, domain is omega, or no, we'll write it like that. So we perform integration by parts for first term. So we transfer derivative to w. Keep this like this, and we have dx here plus keep w as it is. Take antiderivative of this. So we have x1, x2 here. We'll also write x1, x2 here, so we don't cause any confusion. And the other term would stay just like this. And all this will be equal to 0. So what is the weak form we finally got? So basically that's how you take weak form of any differential equation in 1D. So here the derivative requirement is reduced for the psi variable, and this term is here symmetric. Even this one is also symmetric. So yeah, this is the required weak form. Similarly, if we have a 2D equation, so how we take a weak form for this? Again, the basic step is simple. W weight function is divided by the whole equation. And equal to 0. So again, we perform integration by parts on this term. And we get this right here. Sorry. Yeah. I missed this. So we have this plus we have the boundary term coming here. W, sorry, W times and we still have that minus of W times X. So this would be the required weak form for this 2D type of equation. So we have this symmetric term where the derivative requirement on variable u is removed, and we have this boundary term, and we have another term here. So there is no differential requirement on this term, so we don't touch this term here. So we studied divergence theorem, but the simple exercise I came up with to verify the divergence theorem. So what does the divergence theorem say? It's basically so it's transferred as surface integral this is our divergence theorem. So if we can verify separately calculate the left hand side and the right hand side, we can verify this. So first we see the left hand side. If we calculate this divergence of f, so we have what is this gradient is dou by dou x I cap plus dou by dou y j cap dot product with xi cap plus yj cap, and this would give us so this would be partial derivative of, so in dot product we multiply I with I and j with j. So we have a partial derivative of x with respect to x, we'll get 1 here, and then we'll get partial derivative of y with respect to y, we'll get 1 here. So this is the answer. And if we take, so this is not left hand side, sorry, the left hand side is here now. We'll do. So since we are talking in 2D, we have a square surface. So we define the square as x equals sorry, y equals to 0, y equals to 1, x equals to 0, x equals to 1. Before, sorry, 0, 1. So now what we have is basically the volume integral for 2D. So volume integral basically means area. So inside we have 2 dx dy 0 to 1, 0 to 1. So 2 can just go outside. So volume integral of just this basically means the area of the whatever the this 2D object is. So we have square area of square is basically 1 multiplied by 1, that's 2. We'll get 2. Now we follow for right hand side. So right hand side is basically a complicated surface, not too complicated, but we can break it down into 4 surfaces. So for surface 1, so see, this is 1, 2, 3, So for surface 1, what would be the n is basically normal to the surface. So here this normal would be, this is I cap. Here the normal would be j cap. Here the normal would be minus I cap. Here the normal would be minus j cap. So for surface 1 it would be I cap dotted with f. Then we are breaking this whole surface of the square into four surfaces. We have S2. S2 is j cap dot f. Plus we have S3 minus I cap dot f. Plus we have surface integral 4 minus j cap dot f. So for 1, if we take dot product of I with respect with f, so you'll only get x. And for surface 1, if you see, x is constant. X is equals to 1. So we can just write it as 1. And on surface surface S1, y is varying from 0 to 1. So we'll have this integral of with respect to dy 0 to 1. And for 2, we'll have we'll take dot product of f vector f with j, so we only get y, and at surface 2 y equals to 1, you can write 1, and x is varying here from 0 to 1. And similarly for other we have this minus of x, and x is 0 at surface 3, so we'll have 0 dy 0 to 1, and again we have y equals 0 for surface 4, we have 0 dx 0 to 1. So we'll solve this, we get 1, and this will get 1, and other are 0. So finally we'll get 2. So you see the divergence theorem is, so we get 2 at the left hand side and 2 as the right hand side. So this way we can verify by simple problem that divergence theorem is true. Divergence theorem or gradient theorem, simply anything. Okay, so I think it's almost time. We'll wrap it up with this question. So can anyone answer if this operator here? So this operator gradient square on this variable u. So we can say some operator L on u is this. So can you verify if it's linear or not? Can anyone answer here? Think about it. Or so the question is for this equation gradient square u equals 0. I have just for illustration. There's some operator gradient square. This is known as Laplace operator on this variable u. So tell me if this operator is linear or not. So basically some kind of operation is being done on variable u here. So this is the way of representing it. That is basically Laplace operator. So can you tell me if this Laplace operator is linear or not? Yes. So what are the two conditions of linearity? First we need to check both. The first is if we write it the function as u plus p, is it, so if we had applied this operator on a sum of two variables, then what do you call it, it's distributable, right? So this can be distributed on these two functions. We can write it like this. This is valid. And if Yeah, distributive. Thanks. So, and if we have some scalar variable u, so we know that the derivative or this Laplace is nothing but second order derivative. So, if derivative does not work on constants, right? So, alpha is some constant. So we can just simply take out alpha and write it as this. So we see that second condition is verified. So we can say that yes, it is linear. Okay. So all right, then that's it for this session. If there are any questions, then you can still ask. I can extend the session for you. If no, then we can just quit the meeting. We can leave. I'll wait if you still want to ask some question. No doubt. Okay. Thanks, Babu. So it seems that no further doubts are coming. And, okay, so okay, for differential equation, I don't know if there are any books that I know. Let me just check. I studied some book recently, last year I guess, not so recently. Had that book. Differential equation. It's book by Boyce and D. Prema. Elementary differential equation and boundary value problems. I read that a little bit for my comprehensive exam. I'll just share the name with you in the chat. But since you are learning FEM, I don't think you need to worry about solving differential equation because that's what we are going to do. We're going to approximate the solution to these differential equations, and we can deal any type of differential equation problem with this. So I guess you should be patient and focus on this subject more. So you won't have to worry about dealing with differential equations anymore. That's what I would suggest. Anyways, I sent the name of book in the chat. You can take a look at that. Okay, then if there are no more doubts, then can we conclude the session? Okay, then I'll quit the meeting. I stop the recording and quit the meeting. Okay, thank you so much. Thank you so much for your patience.